Hello, here's three more questions on particle physics, nuclear physics, radioactivity. So we're looking here at the fusion of hydrogen nuclei, source of energy in most stars. So here's a typical reaction. We've got two heavy hydrogens going to a light helium and a neutron. So the two deuterium nuclei repel each other. Fusion requires them to get very close, and this occurs at very high temperatures, typically 10 to the 9 Kelvin. So use the data below to calculate the energy released in the fusion reaction above. So we're going to have less mass on the right hand side than on the left. So let's get the difference of that and then plug it into E equals mc squared. So the mass on the left, we've got 2 times, well, everything's got the 10 to the minus 27. So let's leave that out for the moment. 2 times 3.343. And then let's take off what we got on the other side, which is a 5.006, and then take off the 1.675. So what we got there, we got 6.686 minus 6.681. So that's, and then we've got the 10 to the minus 27 that we need to put in as well. So that is 5 times 10 to the minus 30 kilograms, all in all. They've given us some nice friendly numbers. And now the energy is going to be the difference in the mass, which is this, multiplied by speed of light squared. So we've got 5 times 10 to the minus 30 multiplied by 9 times 10 to the 16. So that will be 4.5 times 10 to the, how many have we got all in all here? Minus 13 by the time we take the 10 out of the 45 joules. Cool. State in what form the energy is released. So this is going to be kinetic energy of all of these two on the right hand side. The deuterium nuclei in stars can be modelled as an ideal gas. Calculate the mean kinetic energy of these nuclei at 10 to the 9 Kelvin. Right, so our mean kinetic energy is going to be 3 over 2 kT. That's going to be a little k for Boltzmann constant. So that is 3 over 2 times 1.38 times 10 to the minus 23 multiplied by 10 to the 9. So that is going to be, what's 3 over 2 of that? Because you're going to get 14, so 207 by the time we've done 3 over 2 of that. And then we're going to have 10 to the minus 14, 10 to the minus 14 joules. Excellent. Where are we now? Suggest why some fusion can occur at a temperature as low as 10 to the minus 7. Well, this is the average kinetic energy. So some of the particles, some deuterium nuclei, well, let's just write that, nuclei will have higher than average kinetic energy. Higher than average, higher than the kinetic energy average. So yeah, I think we've done a question very much like this earlier on. It's the same old calculations again, always looking at this this change in mass that we've got as the energy release. All right, up next we've got, oh, it's quite a lot of parts to this one. We've got isotopes of carbon-14 and carbon-15. They're beta minus emitters. So that shows the maximum kinetic energy of electrons emitted and the half-life. Right, state one property common to all isotopes of an element. So that is the number of protons. That's why they are the same element. The neutrons and protons inside each isotope experience fundamental forces. Name the two fundamental forces experienced by both neutrons and protons. Right, so we've got the strong nuclear and gravitational. I mean, there is so the weak force that's kicking around. I mean that's going to be occurring inside these protons and neutrons in between the quarks. Um, so exactly whether you'd rule that out as being experienced by both of them. I mean, they both can be involved in beta minus or beta plus decay, depending on which one it is. So we both got beta decay associated with them, but I think they're probably going for strong nuclear and gravitational here. But there you go. I think there's a case for putting in weak as well. An isotope of carbon-15 decays into an isotope of nitrogen. Complete this nuclear reaction below. Right, well, they've given us pretty much everything, so all we have to do is make the numbers add up. So we're going to have a 7 there, well, A to make it nitrogen, and B to make the proton numbers add up down the bottom, get our charge all adding up, and then at the top, we're going to have a 15 to get our nucleon numbers adding up. Use the quark model to state the changes taking place within the nucleus of a carbon-15 atom. Right, so we need to get an extra proton out of this, out of a neutron. So we've got a neutron, an up, down, down, going to an up, up, down, which is our proton. Right, so far so good. Estimate the maximum speed of an electron from the nucleus of carbon-14. Right, I'm going to start moving up here. I've left this space for I thought some calculations would appear. So maximum speed of what are we? I've forgotten the question now. Electron from the nucleus of carbon-14. Right, so we've got this 0.16 MeV. So that is 0.16 times 1.6 times 10 to the minus 13. And that is our half mv squared. So I'm going to have to go and look up my mass of an electron because I can't quite remember. Well, I might be wrong with it, so let's think. Anyway, so we've got 2.56 times 10 to the minus 14 is a half. See, I reckon it's the 9.11. Is it 9.11 times 9.11 times 10 to the minus 31 multiplied by v squared, just falling off the side of the screen. I'll just double check that is mass of electron. Where's my list? Yep, it is. Excellent. And so rearranging all of this, so 5.12 divided by 9.11 times 10 to the, what would it be, 17 is equal to v squared. So v is coming out as 2.37, so 2.4 times 10 to the 8 meters per second. Suggest why the actual speed of the electron is much less than your answer in this. So we've got our usual relativistic effects. Effects means that the mass will be higher. The faster it goes, the greater the mass. So the mass will increase considerably. So if the mass has gone up, if that number is increased, then our velocity will go down. So v goes down. Right, E. Calculate the decay constant in seconds to minus 1 of carbon-14. Right, okay. E part 1, so our decay constant we know is log 2 over the half-life. So that is going to be log 2. I've finally written down somewhere for reference my seconds in a year to save me typing it all in. So that was the number of years multiplied by 3.16 times 10 to the 7. So we just got to type all of that in. We're getting 3.95 times 10 to the minus 12. So yeah, 4.0 times 10 to the minus 12 seconds to the minus 1. The molar mass of carbon-14 is 14 grams per mole. Show that 1 milligram of carbon has that number of nuclei. Okay, so we've got 0.001 over 14 moles. So we just need to multiply that by Avogadro, 6.02 times 10 to the 23. So that comes out with, I can't be bothered to simplify anything on this. I'm going to go to the calculator because I'm going to have to do this 60.2 over 14 at some point. 4.3, yeah, times 10 to the minus 19. That's good. Calculate the activity of 1 milligram mass of carbon-14. Right, so our activity is just multiplying these two things together. We've got our activity is the decay constant multiplied by the number of nuclei, which is this thing that we just calculated. So just tap those in and we're getting 1.7 times 10 to the 8 per second. Cell decays per second. Final part. Isotope of carbon-14 is very useful in determining the age of a relic, e.g. wooden axe, using a technique known as carbon dating. Describe carbon dating and explain one of its major limitations. Right, there's 3 things that you normally want to say about carbon dating because this comes up so often. So yeah, we've got our 1, 2, 3, and then we've got our limitation. I'm going to struggle to fit this in, but I'm going to obviously talk through it. So we've got living things will absorb carbon dioxide up until when they die. So yes, that's the first thing that we need to do. We need to say something about living things are absorbing CO2 until death. And then we can take the present day ratio. So we need to compare the ratio of carbon-14, I think that should be a ratio sign, to carbon-12 in the sample and in something living. So we need to get those 2 values, and then we can use our decay equation, our n equals n0 e to the minus lambda t, use that in order to work out what the time is. So yeah, we're getting something from the sample is giving us what n is, and the living thing where we haven't had decay going on, we've got the well, at least it's being topped up with the amount of carbon-14. That gives us the n0. So we're then comparing those 2 in that decay equation. But this does assume that the levels of carbon-14 in the living sample aren't different to what they were back in the day. So it's assuming that the ratio hasn't changed with time. That's what we're assuming. So that's one thing. We're also, I suppose, there's a major limitation. There's only so far you can go back because the activity is low. So you can't go too far back in time, otherwise the activity that you're getting from the significantly decayed carbon-14 is so low you just can't really do anything with the measurement. It just sort of blends in with the background measurements you're getting for things. So you can't go too far back in time. We're time limited on it. So yeah, you'll just have to turn those into some kind of sentence. But yeah, it's those 3 things. It's that whole process of all the time something is alive, it's being topped up all of the time with carbon-14. Once it dies, the carbon-14 stops being absorbed, so now you're just getting that decay. We can then compare, well, how much has things got, how much do they start with when they're alive, assuming things haven't changed. Look at something that's living nowadays, and then see how that compares to what's in the sample using our decay equation. But yeah, you have that problem that once you drop below a certain level, you just can't really do that anymore. And we're assuming, as I say, that this starting level hasn't changed. Right, that was a very long question. Right, so hopefully the last one will be a bit quicker. Explain the term binding energy of a nucleus. Right, we've done this quite a few times. So that's the minimum energy to separate all nucleons to infinity. Part B, nuclear fusion takes place in the core of the sun. One of the simplest fusion reactions is this one. Right, okay, so this time we've got 2 heavy hydrogens going to just standard helium, so a little bit different to the one we had last time. Binding energy per nucleon in the hydrogen is that, and in the helium is that. So in binding energy, we're going to have more binding energy on the way out than we are on the way in. So we need to do the binding energy for the helium. So that's going to be 4 times the 1.1 times 10 to the minus 12. So 4.4 times 10 to the minus 12. Take away the binding energy the other side, where, well, again, we've got 2 times 2. So we've got 4 again on that one. So 4 18s is 72, so 7.2 times 10 to the minus 13. That is the energy release. So we've got, what's that going to be? That's going to be 3.68 because we've got a difference in magnitude there. So 3.68 times 10 to the minus 12 joules. So that's done that one. The sun radiates its energy uniformly through space. The mean intensity of the sun's radiation reaching the Earth's atmosphere is, okay, 1400 watts per meter squared. Mean radius of the Earth's orbit around the sun is that. Show that the mean power radiated from the surface of the sun is that. Okay, right, so we've got this sphere. By the time it's got out to a sphere of the radius that is the orbit of the Earth, that is the intensity that we've got. So let's get the surface area of that sphere, which is 4 pi r squared. So that's giving us the area. So we multiply this by the area and it's going to give us the watts. Multiplied by 1400. So that is 4 pi multiplied by, where are we? So that's the radius. So if I square it, 2.25 times 10 to the 22, and then multiply by 1400, which is, oh right, so that's a 10, well not a 10, that's a 9. So we got 9 14s is 126 pi times 10 to the 24. So a bit less to put into the calculator. That is 3.96 times 10 to the 26. So 4 times 10 to the 26. Well, 4.0 I should really put in there for our 2 significant figures. Oh yeah, we were doing a show that. I'd forgotten about that. So carried away in my calculations. Right, assume all the radiated energy from the sun comes from the fusion reaction shown in B. Estimate the number of helium 4 nuclei produced every second by the sun. Okay, so we've got that's the number of joules per second, so we need to divide by the number of joules per reaction in order to get the number of reactions, right? So we're just dividing through by this number here. So we've got 4, or well, 3, let's go back to the 3.96 over 3.68, and that'll be multiplied by 10 to the 38. So that's quite a lot. And well, let's type that in. It's going to be a little more than 1 point, so 0.8, 1.1 times 10 to the 38. So yeah, again, we've done those calculations quite often, although this intensity thing was a little bit new. We haven't had one of those in one of the earlier questions, but it's pretty simple to either think through or just do a unit analysis on it in order to see how we're multiplying things. So yeah, that brings the end of those 3 questions.